Good afternoon, dear colleagues. My name is I'm an independent researcher from Canada. And today I'm going to talk about the analysis of type 1a supernova light curves in observed bands. Type 1a supernovae play an important role of standard candles in modern cosmology due to their consistency of explosions. They also exhibit a phenomenon of light curve broadening, which increases with distance. In 2001, a group of scientists led by Gerson Goldhaber made the conclusion that the light curve stretching of type 1a supernovae is proportional to 1 plus z factor, where z is redshift. In the redshift range of 0 to 1. This group conducted their study using the results obtained by other researchers. So let's review the overall research as a business process. So I'm from IT world, we love business processes there. So here are the steps. Step 1, prepare type 1a at rest spectra series template. So how the spectra changes in typical supernova. 2, observe photometric points in red band. They used 42 supernovae from Supernova Cosmology project. 3, perform K correction. In other words, transform observed magnitude in red band to at rest magnitude in blue band. 4, normalize photometric points in blue band where 1 is a maximum magnitude. 5, using data from nearby supernovae, create normalized light curve template in blue band. 6, build light curves by fitting normalized photometric points to the light curve template. 7, unstretch light curves by factor 1 plus z. 8, build normalized light curve, in other words, place those unstretched light curves to the same coordinate system. 9, because of light curves on this coordinate system match pretty well, make the conclusion about universal time scaling z plus 1. Let's review some of the steps closer. K correction. Take a look at this formula and we can see the usage of 1 plus z scaling factor for time, which is highlighted by red. Fitting to light curve template. This procedure was described by the group led by Sol Perlmutter. They stated the following. For the supernovae discussed in this paper, the template must be time dilated by a factor 1 plus z before fitting to the observed light curves to account for cosmological lengthening of the supernova time scale. As we can see, this business process contains two logical loops where conclusion is used as an assumption. I'm suggesting the alternative process, which is free from K correction and which is free from fitting to templates and therefore does not contain logical loops. Let's briefly go through the steps. Step 1, pretty much the same. Prepare type 1a at rest spectra series template. This is not done by me. 2, simulate light propagation for chosen cosmology model. 3, reconstruct spectra series at observer frame. 4, reconstruct photometric points in observed GRIZ bands. For this research, I used the analysis of data from supernova legacy surveys which was done in GRIZ bands. GRIZ stands for green, red, infrared, and far infrared. To automate steps 2, 3, and 4, I have developed a computer program which is pretty simple. 5. Observe photometric points in GRIZ bands, done in Supernovae legacy survey. 6. Using photometric points, build empiric light curves in GRIZ bands. Yes, I did it myself, by hand, of course using some graphical tools. It is not the best approach, but still better than fitting to templates, because we are not losing the shapes of the light curves. And I hope that researchers will find more elegant ways of doing this in the future, but without fitting. And 7, compare measurements for impeding and simulated light curves. Simulation of light propagation. Here is the main idea. Each photon which departs from a supernova at epoch t, epoch is the day of the explosion, where 0 day corresponds to maximum flux in at rest event. And with wavelength lambda, we'll arrive to an observer at observed epoch t prime, and with wavelength lambda times z plus 1. Then, for any given cosmology model, we should define observed epoch t prime as a function of original epoch t, redshift, and maybe some other parameters. This function can be mathematical or algorithmic. For the standard model, the function is very simple. T prime equals t times z plus 1. So, for this model, any departure pair t lambda will end up at the arrival as t times z plus 1 lambda times z plus 1. What we need is at rest spectra time series templates, and we have them. I use templates prepared by Eric Xiao. And now we can proceed with simulation model. Spectra series template presents flux as a function of t and lambda, where t is departure time, sampled to 100th of epoch, and lambda wavelength binned to 10 angstrom. The original template of Eric Xiao is sampled to 1 day. However, I sampled it to 100th of a day using linear approximation. Formula 1 shows the energy of photon. Then, the number of photons with wavelength lambda at time t will be proportional to the flux divided by photon energy. For simulation purposes, we can define number of issued photons as k times flux times wavelength. Here k is just some arbitrary coefficient. You can choose it just to make your simulation time reasonable. Having two-dimensional array n, we can obtain two-dimensional array n prime at the arrival using the algorithm of 3 nested loops. The algorithm is generic, but the statement highlighted by green is specific for a chosen cosmology model. In this case, it's very simple. T prime equals t times z plus 1. Simulation results. Having array n prime as a result of the simulation program, we can reconstruct spectra series at observed frame using formula 4. Here, tau is transmittance related to light extinction in our galaxy for wavelength lambda prime, derived from Cardelli law for Milky Way. The photometric points at observer frame in observed bands, such as grease, can be determined by Formula 5. Here R is transmittance of the band filter corrected for telescope response for wavelength lambda prime. Parameters. What parameters I compared? In this research, I selected the following parameters for comparison between observed data and simulated data. You can select any other parameters that can be derived from light curves or spectra. First parameter is the curve width on the level of a half of maximum flux. And the second parameter is the ratio between width of the rising part to width of the falling part. This slide shows the example of simulated light curve, which is built for I band and for redshift 0.8. And here are some examples of empirical light curves that I built based on observed photometric points. After measuring parameters, we can build their dependencies on redshift. Oops. Okay, here's the example of light curve width in R band. So we can see that red color indicates simulated time dilation, which is basically predicted by standard cosmology, and blue line is regression built for measurement on observed curves. As we can see, they don't match well. Here's the light curve width in I band. They don't match again. Z band, discrepancy is smaller, but still they don't match. So, as we can see in all bands, there are discrepancies between observed and simulated, in other words, predicted dependencies of light curve width on redshift. Before we move further, let me share some facts from queuing theory. Let's consider some hypothetical example. Imagine travelers who depart from a departure point and arrive at an arrival point. Assume that departure rate, which is number of departures per second, changes with time, and this change in time has a shape of a bell. If traveling time is random, even to little extent, then the arrival rate also will have bell shape. However, the maximum rate will be lower and the bell will be wider. In the case B, we have departure rate change asymmetrical. What will happen at arrival? Again, the maximum flux will be lower, the shape of the bell will be wider, but additionally to that, the arrival bell will be less asymmetrical, which is very important. In terms of measured values, we can say that the ratio between width of the rising part to width of the falling part will become greater. And these are mathematical facts. So how it's all related to supernovae? Essentially, a light curve of supernova in original frame represents the change of the departure rate of photons, and light curve in observed frame represents the change of the arrival rate. Now let's see our comparison. This is rise to fall ratio in G band. Not much difference, but from another point of view, we don't have that many measured points in G band. In R band, mainly observed glue dependency is mostly higher. In I band, it's also a little bit higher, but most interesting is Z band. Why is that? Because the light curve in the corresponding band in the original supernova frame is most asymmetrical among considered bands. It is the Z band where we most likely will observe the change in the rise to fall width ratio if traveling time is variable. And look at this picture. We have clear and consistent difference between blue and red curves, and this is very compelling result. Variability of speed of light was predicted by scientists in the field of quantum physics. They state that vacuum is a complex medium which is subjected to various physical processes, and therefore speed of light cannot be a constant. Within this research, we can see that supernovae provide us with the evidence for these predictions. In summary, there is no universal Z+1 light curve broadening. Light curves widen differently in different bands and for different redshifts. Rise to fall width ratio in Z band gives us an evidence that real speed of light is not constant. Unstable speed of light is one of the reasons for light curve broadening and dimming of supernovae at high redshifts. And final slide, my proposals to NASA. So in 2013, NASA made a call for proposals for the roadmap for fundamental research till 2030. I've submitted my proposals and they were published on NASA website. Here are some of them. Measurements of photometric points in infrared and far infrared bands are as important as invisible bands. Photometric points to be measured more frequently. Spectral measurements should be done not only to confirm type of supernova, but at different stages of supernova explosion. And final recommendation, the results of observations should be accessible in public domain at all stages. For raw data and data after any stage of processing. Please support. Thank you very much for your attention. I'm sure that supernova will bring us more exciting